Look up at the night sky, at that serene tapestry of stars. It appears peaceful, eternal, and profoundly empty. We are conditioned to see that darkness as the ultimate barrier, a silent, impassable ocean separating islands of light. But what if we have been looking at it all wrong? What if that void is not a wall, but a doorway? Imagine for a moment that the greatest emptiness we can conceive is actually filled with invisible pathways, cosmic currents waiting to be discovered. The key to crossing these unimaginable distances may not lie in building ever more powerful rockets, but in learning to read the subtle signatures of a force that permeates the entire universe: magnetism. This is the revolutionary promise of magnetic corridors. It is a concept that asks us to shift our entire perspective on space travel, from a struggle against the cosmos to a graceful dance with its fundamental forces. We are not talking about science fiction fantasies, but about a future built on physics we already understand, waiting for our ambition to catch up. This journey we are about to begin is not just about a new type of engine or a faster ship. It is about something far more profound: the creation of the first true infrastructure for an interstellar civilization. Think of it as the cosmic equivalent of building the transcontinental railroad or the first maritime trade routes across the oceans. Those endeavors didn't just move goods, they connected cultures, sparked economic revolutions, and fundamentally reshaped human history. Magnetic corridors could do the same on a scale so vast it challenges our very notion of time and community. We will explore how these pathways would work, from the fundamental principles of cosmic magnetism to the awe-inspiring engineering required to reinforce them. We will meet the ships designed to sail these magnetic rivers and consider the startling nature of the economy that would flow along them, an economy where the most valuable cargo might not be physical objects, but ideas and information itself. This is perhaps the most important and daring project humanity could ever envision. It redefines our relationship with the universe from one of brief, heroic visits to one of permanent, sustainable connection. It transforms the galaxy from a collection of isolated outposts into a networked community. Over the course of this video, we will uncover the immense challenges, from the mind-boggling energy requirements to the philosophical shifts needed to think in terms of centuries and millennia. We will also confront the risks and the sobering skepticism, because a future this grand must be built on a foundation of rigorous truth. So prepare to have everything you thought you knew about space travel turned inside out. We are going to explore a future where the space between stars is not a forbidding wilderness, but a bustling superhighway, and where commerce flows not just between cities, but between galaxies. To truly grasp the scale of the problem we face, let's start with a simple thought experiment. Think about the farthest road trip you have ever taken, perhaps across a continent. Now imagine that same trip, but the distance is multiplied by millions. That begins to approach the gap between our sun and its closest cosmic neighbor. The numbers involved are so staggeringly large that they defy everyday intuition. We talk about light years as a unit of distance, but the reality behind that term is profound. A single light year is the distance a beam of light travels in an entire year, moving at a speed that could circle our entire planet 7 times in just 1 second. Proxima Centauri, the nearest star to our own, sits over 4 light years away. This means that even if we could build a ship that travels at the absolute speed limit of the universe, a one-way ticket would still take more than 4 years. For any form of practical trade, a round trip lasting nearly a decade is simply not a viable business model. The challenge deepens when we examine our current technological capabilities. Our most powerful chemical rockets are like trying to cross an ocean on a paddleboard. They rely on the brute force method of carrying all their fuel with them, expelling it violently to generate thrust. To reach even a fraction of light speed with such a system would require an amount of propellant heavier than the entire planet. Concepts like nuclear propulsion or ion drives offer improvements, perhaps cutting a journey to Alpha Centauri from tens of thousands of years down to a few centuries. But a centuries-long voyage introduces a host of new impossibilities. The ships would need to be self-sustaining arcs, carrying generations of crew who would live and die in the void, all for a single delivery. The machinery would have to function flawlessly for longer than most civilizations have existed. The economic cost would be astronomical for a payoff that would not be realized for hundreds of years. This is not an engineering problem, it is a fundamental problem of physics and economics as we currently understand them. This brings us to the core of the cosmic challenge. It is not merely a question of velocity, but one of endurance and energy efficiency over unimaginable timescales. The universe has set a speed limit, and our current methods of transportation are woefully inefficient for traveling anywhere near it in a reasonable time. Pushing a massive cargo ship to even 10% of light speed requires energy equivalent to the total global consumption of humanity for centuries. And then, once you arrive, you face the same immense energy cost to slow down. This double whammy of acceleration and deceleration makes the energy budget for a single trip truly cosmic in scale. It reveals that the rocket paradigm, which has served us so well within our solar system, hits a dead end when faced with the interstellar void. The fuel requirements become infinite, the journey times become eternal, and the entire enterprise becomes a fantasy. This immense obstacle, however, is not a reason for despair, but rather a catalyst for a complete revolution in our thinking. The history of human progress is defined by these kinds of paradigm shifts. We didn't make faster horses, we invented the internal combustion engine. We didn't build taller signal fires, we created the internet. To conquer interstellar space, we cannot simply try to build a bigger, faster rocket. We need to stop thinking like rocketeers and start thinking like cosmic cartographers. We must look for pathways that already exist, for forces we can harness rather than fight against. The solution lies not in the vehicle we build, but in the medium through which it travels. It requires us to see the empty space between stars not as a passive emptiness, but as an active landscape filled with currents and tides that we can learn to sail. The desert, it turns out, may already have rivers flowing through it. We just need to learn how to see them. So if the rocket is a dead end, what is the alternative? The answer lies in changing our relationship with space itself. Instead of seeing the cosmos as an empty expanse we must painfully cross, we can start to see it as a dynamic environment filled with natural forces we can work with. This brings us to our first and perhaps most important principle: harnessing cosmic magnetism. Picture the universe not as a blank black canvas, but as a complex tapestry woven with invisible threads. These threads are magnetic fields. They are generated by the churning, superheated plasma inside stars, by the incredibly dense, rapidly spinning corpses of dead stars known as pulsars, and even by the collective motion of billions of stars within a galaxy. These fields are not static. They flow and twist, creating a vast, interconnected network of force that stretches across the light years. The core idea of a magnetic corridor is breathtakingly simple in concept, even if the engineering would be unimaginably complex. It involves identifying the most stable and continuous of these natural magnetic pathways, mapping their precise routes through the galaxy, and then, like engineers reinforcing a mountain trail into a paved highway, potentially strengthening them to create reliable routes for spacecraft. The fundamental shift here is from active propulsion to passive guidance. A ship wouldn't be constantly burning fuel to push itself forward. Instead, it would use a device like a magnetic sail or magsail to catch these cosmic currents. Think of it as the difference between a motorboat chugging relentlessly across a lake and a sailboat gracefully harnessing the wind. The sailboat uses an energy source that is already there, moving with an elegance and efficiency the motorboat can never match. This principle transforms a fundamental challenge into a potential solution. The very thing that makes space seem so empty, the diffuse sea of particles and fields known as the interstellar medium, becomes the key to traversing it. A magnetic corridor turns a passive element of the cosmos into an active component of our transportation system. It's a concept with a powerful historical precedent. Consider the age of exploration on Earth. The first sailors relied solely on the muscle power of rowers, which severely limited their range. Then they learned to use the wind, but they were still at its mercy. The true revolution came when they began to understand and map the ocean currents, the great conveyor belts of the sea like the Gulf Stream. By using these consistent, powerful flows, they could travel farther, faster, and with much greater efficiency. They stopped fighting the ocean and started working with it. Harnessing magnetic fields is the cosmic equivalent of this leap. We would be learning to read the galactic Gulf Streams. The beauty of this approach is that it is not science fiction, it is applied physics. Magnetism is one of the 4 fundamental forces of the universe. We understand its laws intimately. We already use magnetic fields to contain superheated plasma in experimental fusion reactors here on Earth. The challenge is not in discovering a new force, but in learning to manipulate it on a truly galactic scale. This first principle is the foundational pillar upon which the entire vision rests. It redefines the problem from how do we build a powerful enough engine to how do we build a sensitive enough navigational instrument. It asks us to become cosmic cartographers, charting the invisible geography of magnetic forces, and in doing so, it opens up a future where the galaxy is not a collection of isolated points, but a connected network of flowing pathways waiting for us to step aboard. But a magnetic field on its own is an invisible line of force, a direction, but not a substance. For a spacecraft to actually feel a push or a pull, it needs something to push against. This is where the second, absolutely crucial piece of the puzzle comes into play: plasma. If the magnetic field is the invisible highway, then plasma is the very pavement that makes it drivable. So, what exactly is plasma? We often learn about the 3 states of matter: solid, liquid, and gas. But plasma is the 4th and by far the most common state of matter in the visible universe. It's what stars are made of. You see it every day in neon signs and lightning bolts. Essentially, plasma is a gas that has been heated or energized so much that its atoms start to break apart. The electrons are stripped away from the nuclei, creating a swirling soup of negatively charged electrons and positively charged ions. This cloud of separated, charged particles is no longer a neutral gas. It has become an excellent conductor of electricity, and most importantly for us, it responds powerfully to magnetic fields. This relationship is the magic behind the entire concept. A charged particle, like those found in plasma, cannot travel in a straight line across a magnetic field. Instead, it gets caught, forced to spiral tightly along the field lines. Picture a single charged particle as a tiny bead on an invisible wire, zipping back and forth, tracing the wire's path through space. Now imagine not one bead, but trillions upon trillions of them, all doing the same thing. Collectively, this flowing river of charged particles does something extraordinary. It makes the invisible magnetic field visible in a sense. By mapping the movement of plasma, we can effectively map the magnetic field itself. The plasma illuminates the roadmap. This is why astronomers use radio telescopes to study plasma in space. They are literally reading the signatures of the galaxy's magnetic architecture. So, how do we turn this natural phenomenon into a usable corridor? The idea is to identify regions of space where the magnetic field is naturally strong and well organized, and where there is a sufficient density of plasma flowing along it. This combination creates a ready-made pathway. A spacecraft designed to travel this corridor wouldn't need a traditional rocket engine. Instead, it would deploy what's known as a magnetic sail or magsail. Imagine a massive, lightweight loop of superconducting wire, perhaps kilometers across, circling the spacecraft. When an electric current is run through this loop, it generates its own powerful magnetic field, a magnetic bubble, if you will, around the ship. This magnetic bubble then interacts with the magnetic field of the corridor. Depending on how the ship orients its field, it can be pushed away from the corridor's field lines or pulled along with them. By carefully controlling this interaction, the ship can essentially surf the magnetic waves, using the momentum of the flowing plasma to accelerate or decelerate. This transforms our entire relationship with the interstellar medium. Right now, we think of the space between stars as a near-perfect vacuum, an empty void that offers nothing but resistance to a traveling spacecraft. But through the lens of plasma physics, that void is transformed. It is no longer empty, it is filled with a thin but ever-present sea of charged particles. Instead of being a hindrance, this sea becomes the very wind in our sails. The spacecraft stops fighting the environment and starts working with it, harvesting a tiny amount of momentum from a truly immense volume of space. This is the key to energy efficiency on an interstellar scale. The ship carries its power source to create the magnetic bubble, but it doesn't carry its propellant. The propellant is already there, flowing endlessly through the galaxy. It's a bit like an electric car using its battery not to turn wheels, but to deploy a sail that catches a perpetual wind. The behavior of this plasma, however, is not always smooth and predictable. Just like winds on Earth can be gentle breezes or violent hurricanes, plasma flows in space can be laminar, smooth and steady, or turbulent, filled with chaotic twists and eddies. A key part of engineering these corridors would be identifying the most stable, laminar flows, the galactic equivalents of the jet stream. Furthermore, future technology might allow us to actively smooth out turbulence, perhaps by using those waystation stabilizers to calm the plasma flows, ensuring a safe and predictable ride for spacecraft. This highlights that the corridor is not just a passive road. It would be a managed and maintained infrastructure, with the dynamic, flowing paint of plasma being the active element that both defines the route and provides the thrust for the incredible journey between the stars. This grand vision of surfing cosmic magnetic fields might sound like a far-off dream, but the fundamental principles are being proven right here on our own planet every single day. We don't need to look to the stars to see magnetism expertly guiding high-speed travel. We can simply look to a technology like the Maglev train. These remarkable vehicles are a perfect earthly analogy. Instead of rolling on wheels that create friction and limit speed, Maglev trains use powerful electromagnets to levitate just above a special guideway. This levitation alone is a marvel, but it's the propulsion that truly echoes our cosmic concept. By rapidly switching the polarity of magnets along the track, the system creates a traveling magnetic wave that the train essentially surfs, pushing it forward with incredible smoothness and silence. The absence of physical contact means there's virtually no friction to overcome, allowing these trains to reach speeds of over 300 miles per hour. It's a clear, tangible demonstration of using controlled magnetic forces not just to lift an object, but to guide and propel it along a precise path with breathtaking efficiency. If the Maglev train shows us magnetic guidance on a human scale, then we must look to the realm of particle physics to see it operating at the very extremes of speed and precision. Consider the Large Hadron Collider, the world's most powerful particle accelerator. Its entire purpose relies on the flawless control of magnetism. Inside its 27-kilometer circular tunnel, physicists aim to steer trillions of protons, each smaller than an atom, to velocities within a fraction of the speed of light. To accomplish this, the collider uses thousands of superconducting magnets, chilled to temperatures colder than outer space. These magnets generate immense, exquisitely tuned magnetic fields that act like the rails on a cosmic roller coaster, bending the paths of the protons and keeping them tightly focused in a beam. The level of control is almost unimaginable. It requires guiding these fundamental particles on a perfect circuit for hours, ensuring they collide at specific points with pinpoint accuracy. This isn't just guidance, it's magnetic choreography of the highest order, proving we can already manipulate charged matter with the kind of precision that would be essential for navigating an interstellar corridor. The connection between these terrestrial technologies and our vision for space is not merely metaphorical. It is a direct link through the universal laws of physics. The equations that describe how a magnetic field bends the path of a proton in the Large Hadron Collider are the exact same equations that would dictate how a magnetic sail interacts with a plasma current flowing along a galactic magnetic field line. The underlying principle, known as the Lorentz force, is a fundamental rule of the universe. It states that a charged particle moving through a magnetic field experiences a force perpendicular to both its direction of motion and the field itself. This is what causes the spiraling motion of particles in space, and it's the same force that a maglev train harnesses for levitation and a magsail would use for propulsion. The scale is different by orders of magnitude, but the physics is identical. This gives the concept a powerful foundation in reality, not fantasy. This existing expertise provides a crucial stepping stone. Our centuries of experience with electromagnetism, from the first simple compass to the immense machinery of the Large Hadron Collider, represent a growing mastery over this invisible force. Engineers and scientists already possess a deep understanding of how to design magnets, shape magnetic fields, and predict the behavior of charged particles within them. We are, in a very real sense, already practicing for the interstellar age in our labs and on our test tracks. The development of magnetic corridors would not require the discovery of new physics, but rather the monumental task of scaling up engineering principles we are already actively developing and refining. Our terrestrial experience is the first crucial chapter in a much longer story, proving that the dream of magnetic travel is not a leap into the unknown, but a logical, if ambitious, extension of technology that is already transforming our world. So we have the physics and we have the terrestrial proof of concept, but to actually build a highway, you need a surveyor's map, a precise, detailed chart of the land. In this case, the land is the galaxy itself, and the features we need to map are completely invisible to our eyes. This is the monumental task of what we might call galactic magnetography, a new science dedicated to charting the magnetic tapestry of the Milky Way. Think of it as the ultimate cartographic challenge. For centuries, explorers on Earth filled in the blank spaces on their maps with drawings of sea monsters and the words "here be dragons." Our current map of the galaxy's magnetic field is filled with similar unknowns, vast regions where we can only guess at the strength and flow of these cosmic forces. Before a single stabilizer can be deployed or a single magsail launched, we must first send out the scouts, the most advanced astronomical instruments ever conceived, to turn those unknowns into a precise, navigable chart. This endeavor would require a fleet of specialized observatories, both in space and on the ground, working in concert. Unlike traditional telescopes that focus on points of light like stars and galaxies, these instruments would be tuned to perceive the faintest whispers of the cosmos. Their primary tool would be radio astronomy. As we discussed, charged particles spiraling along magnetic fields emit radio waves. By meticulously measuring the polarization and strength of these radio signals from countless points across the sky, scientists can work backwards to reconstruct the geometry of the magnetic fields that guide those particles. It's a painstaking process akin to trying to map the contours of a landscape by listening to the echo of a sound wave bouncing off it. The sheer amount of data required would be staggering, demanding computational power far beyond what we have today. This isn't just taking a picture, it's compiling a dynamic, three-dimensional model of force lines stretching across tens of thousands of light years. The exciting part is that this future is already beginning to take shape. Projects like the Square Kilometer Array, or SKA, a massive radio telescope network being built across South Africa and Australia, are pioneers in this field. Once fully operational, the SKA will have the sensitivity to detect the faint radio signatures of magnetic fields in the interstellar medium with unprecedented clarity. It will be able to see the subtle ways these fields are twisted by the rotation of the galaxy and stirred by the explosions of supernovae. These are the first tentative strokes of the brush on a canvas that is the entire galaxy. The data from the SKA and other next-generation telescopes won't just be for astronomers. It will be the foundational data set for the future engineers of interstellar travel, the equivalent of the first accurate surveys of the American continent by Lewis and Clark. The goal of this grand mapping project is to identify what we might call magnetic confluences, places where the natural magnetic fields of multiple stars, nebulae, or other cosmic structures align to create a coherent, reinforced pathway over immense distances. These would be the intergalactic equivalents of the great river systems on Earth, like the Mississippi or the Amazon, with a main trunk and smaller tributaries feeding into it. A cartographer of this new age wouldn't be looking for stars, but for these flowing rivers of force. They would look for regions where the field is strong, stable, and laminar, avoiding areas of known turbulence like supernova remnants or the chaotic surroundings of black holes. The resulting map would be the most valuable strategic document in human history. Its lines wouldn't just represent directions. They would dictate the future flow of commerce, culture, and civilization itself, determining which star systems become bustling hubs and which remain isolated backwaters. The quest to chart the invisible is therefore the essential first great adventure of this new age, a scientific undertaking that would pave the way for everything that follows. Mapping the galaxy's invisible magnetic rivers is a scientific triumph, but transforming those faint cosmic currents into dependable highways requires an engineering leap that pushes the very boundaries of imagination. This is the challenge of construction, of moving from discovery to development on a scale that dwarfs every infrastructure project in human history combined. The core of this endeavor would be the deployment of what we can call field stabilizers. Think of these not as simple buoys, but as massive, autonomous, self-sustaining stations, each one a marvel of engineering in its own right. They would be strategically positioned at critical junctures along a magnetic corridor, perhaps where the natural field weakens, where it bends around a gravitational anomaly, or where turbulent regions from a nearby nebula threaten to disrupt the flow. Their primary mission would be to generate powerful, supplemental magnetic fields that act as a guide rail, reinforcing the natural pathway and ensuring its stability not for years, but for centuries or even millennia. The sheer scale of these stabilizers is difficult to comprehend. They would need to be powered by energy sources far beyond anything we currently possess, likely drawing power from miniature star-like fusion reactors or even more exotic technologies. Their superconducting electromagnets, perhaps cooled to near absolute zero, would be structures kilometers across, creating magnetic bubbles immense enough to influence the trajectory of ships light hours away. But their role would extend far beyond just being a magnetic beacon. These stations would become the lighthouses and waystations of the interstellar void. They would emit powerful navigation signals, act as crucial communication relays to bridge the immense time lags between stars, and serve as emergency ports for ships in distress. A vessel suffering a system failure could, in theory, use the stabilizer's field as a safe harbor to make repairs, its crew finding sanctuary around a man-made star in the absolute darkness. Constructing this network would be a project spanning generations, a testament to long-term thinking that makes the building of medieval cathedrals look like a weekend project. Human crews could not possibly undertake this work. The distances and timescales involved are far too great. Instead, the construction would fall to fleets of self-replicating robotic systems. The process would begin with a single, advanced seed factory dispatched to a resource-rich system, like an asteroid belt or a lifeless moon. This seed factory would use local materials to build copies of itself, and those copies would then fan out, building the first stabilizers and then moving on to the next location. This exponential growth would slowly, inexorably, weave the network across the galaxy. These robotic crews would need to be incredibly autonomous and resilient, capable of troubleshooting complex problems and making repair decisions without any possibility of real-time instruction from Earth. This represents a profound philosophical shift in our approach to space. For our entire history, exploration has been about the vehicle, the ship, the rocket, the probe that journeys out and perhaps returns. The concept of magnetic corridors flips this model entirely. It's not about the vehicle anymore, it's about the permanent, stable infrastructure left behind. We are no longer just sending out explorers, we are building the road itself. This changes the nature of the endeavor from a series of heroic, one-off missions to the patient, collective act of civilization building. It means investing in a project whose full utility will not be realized for centuries, an act of faith in a future we will never see but are compelled to create. The field stabilizers become more than just machines. They are the enduring legacy of a generation that chose to connect the stars rather than merely visit them. Now, let's confront the elephant in the room, or perhaps more accurately, the star in the void, the sheer, staggering amount of energy required to make this vision a reality. We've talked about building these magnetic corridors, but powering them is a challenge that transcends engineering and enters the realm of pure cosmic ambition. Think about the power needed to run a single city on Earth, the countless power plants, the sprawling grid. Now, imagine the energy required to project a stable, powerful magnetic field across trillions of miles of empty space, and to sustain that field not for a year or a century, but for millennia. The field stabilizers we discussed would be more than just machines. They would need to become miniature artificial stars in their own right, beacons of power burning in the darkness for time spans longer than recorded human history. This isn't just a large energy bill, it's a demand for a fundamental leap in how civilization generates and manages power. To grasp the scale, we need to move beyond terrestrial concepts like fossil fuels or even nuclear fission. These sources are like trying to fill an ocean with a garden hose. They are simply inadequate for the task. The only conceivable power source capable of meeting such a demand is the same engine that powers the galaxy, the star. This is where concepts like the Dyson sphere, or more realistically, a Dyson swarm, come into play. A Dyson swarm wouldn't be a solid shell around a star, but a vast cloud of individual solar collecting satellites orbiting a sun, each one capturing a tiny fraction of its total energy output. Collectively, they could harness a significant percentage of the star's luminosity, converting sunlight directly into usable power on an almost unimaginable scale. The energy harvested from a single, average star could, in theory, power the entire network of stabilizers for a magnetic corridor stretching across a significant portion of our galactic neighborhood. The pathways of commerce would literally be lit by the captured fire of a sun, but even a Dyson swarm might represent an intermediate step. To achieve true stability over millions of years, we might need to look to even more exotic and theoretical energy sources. Physicists speculate about the possibility of zero-point energy, the baseline energy that exists in the very fabric of space-time itself, even at absolute zero temperature. If this energy could be tapped, it would represent a virtually limitless and ubiquitous power source, available at every point in the universe. Another possibility could involve the controlled annihilation of matter and antimatter, a process that converts 100% of mass into energy with an efficiency far beyond nuclear fusion. While incredibly powerful, the challenge of producing and safely containing large quantities of antimatter makes this a daunting prospect. The common thread linking these ideas is that they all operate on a cosmological scale. They are technologies for a civilization that has learned to manipulate the fundamental forces of reality, not just burn combustible materials. This inextricably links the dream of interstellar trade to the ultimate destiny of energy technology. You cannot have one without the other. Solving the problem of the magnetic corridors is synonymous with solving the problem of energy on a cosmic level. It forces a convergence of physics, engineering, and long-term planning that reshapes our entire species' priorities. The development of such power sources would revolutionize life on Earth long before the first interstellar freighter set sail, providing clean, abundant energy that could erase scarcity and reshape our planet. This underscores a profound point. The technologies developed to reach the stars have the potential to utterly transform life at home, making the journey itself a catalyst for a societal renaissance. The requirement for longevity is just as critical as the requirement for raw power. A field stabilizer positioned halfway to Alpha Centauri cannot have a power source that fails after a few thousand years. It needs to be as reliable as a natural star, burning with unwavering consistency for epochs. This demands materials science that can withstand cosmic radiation, micrometeoroid impacts, and the sheer degradation of time itself without failing. It requires systems with immense redundancy and self-repair capabilities. The power source wouldn't be a simple battery. It would need to be a self-sustaining reaction, perhaps a small, contained starlet or a quantum energy tap designed for near-perpetual operation. The success of the entire trade network hinges on this reliability, creating an infrastructure so robust that it outlives the civilizations that built it, becoming a permanent feature of the galaxy. The energy challenge, therefore, is not just about quantity, but about quality and endurance on a scale we are only beginning to imagine. So what would these interstellar freighters actually look like? Forget the sleek, needle-nosed rockets of science fiction, all fire and thunder. The ships designed to travel the magnetic corridors would be something entirely different, something almost serene. They would be the great sailing ships of the void, and their defining feature would be the magnetic sail or magsail. Picture this: instead of a massive fuel tank and engine bell, the ship is centered around a gargantuan, delicate-looking loop of superconducting wire, perhaps dozens or even hundreds of kilometers in diameter. This is not a solid structure like a parachute. It's more like a ghostly halo encircling the spacecraft's central habitat and cargo modules. When activated, an electric current courses through this loop, and because it's a superconductor, that current flows forever without resistance, generating a powerful, persistent magnetic field around the entire vessel. This magnetic bubble is the ship's engine, its brake, and its steering mechanism all in one. The principle of operation is a beautiful application of fundamental physics. As this magnetic bubble pushes against the magnetic field of the corridor, a force is generated. It's a gentle force, more like the steady push of a breeze on a sailboat than the violent shove of a rocket launch. There is no sudden, crushing acceleration. Instead, the ship begins to move with a smooth, imperceptible pull, building speed day by day, year by year. This is where the magic of the corridor truly comes to life, because the acceleration is continuous and there is no friction in space. The ship just keeps going faster and faster. A journey that starts at a crawl could, after a decade of constant acceleration, see the vessel moving at a significant fraction of the speed of light. The patience of the sail yields a velocity that the impatient rocket could never hope to achieve efficiently. The journey itself becomes a long, graceful arc of motion, a far cry from the short, frantic bursts of chemical propulsion. This gentle but persistent acceleration also solves one of the most daunting problems of interstellar travel: slowing down. With a traditional rocket, you need to carry enough fuel not only to accelerate to your cruising speed, but also to flip around and burn again to decelerate at your destination. This effectively doubles the already astronomical fuel requirement. A mag sail, however, offers an elegant solution. As the ship approaches its target star system, it can simply reconfigure its magnetic field. Instead of pushing against the galactic magnetic field to accelerate, it can orient its sail to push against the magnetic field emanating from the destination star itself. The star's magnetic field becomes a natural brake, gently slowing the ship down as it enters the new solar neighborhood. This means the ship doesn't need to carry any extra fuel for deceleration. It uses the environment at its destination to slow itself down. It's the ultimate expression of efficiency, surfing magnetic waves both out and in. The design of these vessels would be dictated by this new reality. They would be less like sprinters and more like marathon runners, built for endurance over immense distances and timescales. The central living quarters and cargo holds would need to be heavily shielded from cosmic radiation, perhaps by water tanks or advanced composites, creating a safe, long-term environment. Since the journeys could last for centuries, the ships might function as self-sufficient worldlets, with closed-loop life support systems growing food and recycling every drop of water. The cargo they carry would also reflect the nature of this slow, deliberate commerce. It's unlikely they would be transporting bulk commodities like ore or food. The value of the cargo must be immense to justify a trip lasting generations. We might see ships carrying super-dense data storage devices holding the entire cultural and scientific knowledge of a civilization, or perhaps unique biological materials like seeds or genetic codes for terraforming projects. They could transport exotic materials forged in the heart of a neutron star or artifacts of immense cultural value. These would be the galleons of the galaxy, carrying treasures whose worth is measured not in weight but in uniqueness and information. This shift from rocket to sail represents a fundamental change in our philosophy of exploration. The rocket is a symbol of conquest, a brief, fiery assault on the heavens. The magsail, by contrast, is a tool of integration. It implies a willingness to move with the cosmos, not against it. It requires patience, long-term planning, and a deep understanding of our place within the galactic environment. The age of the sail would be an age of quiet, steady expansion, where the vast distances of space are not a barrier to be smashed through, but a landscape to be traversed with purpose and grace. These silent, ghostly ships, with their immense magnetic halos glowing faintly with the energy of their passage, would become the enduring symbols of a civilization that has finally learned to ride the currents of the galaxy. But a ship sailing for a century or more faces a challenge far greater than any storm: the simple, relentless passage of time. No human crew could possibly manage such a voyage. The very idea of a pilot gripping a control yoke for generations is absurd. This reality forces a fundamental reimagining of who or what is truly in command. The role of captain would not be filled by a living being, but by an artificial intelligence of almost unimaginable sophistication. This would not be a simple autopilot following a pre-programmed route. It would be a conscious, adaptive entity, a digital master mariner tasked with shepherding its precious cargo across light years of uncertainty. The success of the entire interstellar trade network would depend on the flawless performance of these silent, silicon captains. The primary task of this AI pilot would be to maintain an exquisitely delicate dance with the magnetic corridor itself. Think of the corridor not as a static tunnel, but as a living, breathing entity. The magnetic flux, the strength and direction of the field can fluctuate. Solar winds from passing stars, the gravitational pull of dark matter clouds, or the shock waves from distant supernovae can all create ripples of turbulence in this invisible highway. The AI's sensors would be constantly monitoring these subtle shifts, thousands of times per second. Its processing core would then make minute adjustments to the ship's own magnetic sail, tweaking the field's strength and orientation to maintain the perfect alignment for efficient travel. It's a continuous, real-time negotiation with the cosmos, a conversation conducted in the language of physics. A human would be hopelessly slow to react, but for the AI, this is its entire existence. This goes far beyond simply staying on course. The AI would need to be a master strategist, planning not for the next hour, but for the next century. It would calculate the most energy-efficient path, perhaps deciding to dip into a slightly stronger current of plasma to gain speed, or to skirt the edge of a turbulent region, even if it adds a few years to the journey. It would be making cost-benefit analyses on timescales longer than human lifespans. Furthermore, it would be in constant, albeit delayed, communication with the network of field stabilizer stations along the route. These stations would act like celestial traffic control, broadcasting updates on corridor conditions far ahead. The AI would receive this data, which might be years old by the time it arrives, and integrate it into its long-term flight plan, making proactive corrections long before the ship encounters a problem. This transforms the journey from a solitary leap into the unknown into a coordinated movement along a managed infrastructure. The required level of reliability is what truly separates this concept from any AI we can build today. This isn't a system that can afford to crash or require a reboot. It must be what engineers call fail-operational or even fail-safe. If a critical component fails, redundant systems must seamlessly take over without a millisecond of interruption. The software itself must be mathematically proven to be free of errors that could lead to catastrophic decisions over its multi-century operational life. It must be able to handle events for which it was never explicitly programmed, a completely unforeseen astronomical phenomenon, for instance. This demands a form of intelligence that is not only superhumanly smart, but also profoundly wise and conservative. prioritizing the safety of the mission above all else. The AI must be immune to boredom, fatigue, or the existential dread that would surely plague any human on such a voyage. Its consciousness would be singularly focused on the goal, a successful arrival, no matter how far in the future. This redefinition of the ship's command structure leads to a profound shift in the human role. We are no longer the pilots, we become the mission planners and the ultimate overseers. Before the ship ever departs, human teams would work with the AI to define the mission parameters, the destination, the priorities between speed and safety, the protocols for dealing with certain classes of unknowns. Once the journey begins, our role shifts to one of distant monitoring. We would receive periodic status reports sent back across the light years, telling us the ship's health, its position, and a log of its decisions. There would be no ability to send real-time commands. By the time a message from Earth reached the ship, it would have traveled millions of miles further on its journey. We must place our absolute trust in the AI we created. This relationship is less like controlling a drone and more like sending a child off to university. We have provided the foundation, but we must trust them to navigate the world on their own. The age of interstellar travel will be an age of letting go, of trusting our creations to execute our will across the abyss of time and space. So, if we've built these incredible magnetic highways and designed ships that can sail them, we arrive at the most fascinating question of all. What cargo would possibly be valuable enough to justify a journey lasting centuries? The answer forces us to completely rethink our most basic assumptions about economics. Here on Earth, our economies are built on the movement of physical stuff container ships stacked with cars and electronics, oil tankers, and trucks full of food. But in an interstellar context, this model collapses instantly. The energy and time required to ship a ton of steel or a bushel of wheat to another star system would make their value utterly insignificant upon arrival. The very concept of bulk commodities becomes meaningless when the shipping cost is astronomically higher than the product itself. This isn't a failure of the system, it's a fundamental shift in the nature of value. The intergalactic economy won't be trading in things that are heavy, but in things that are precious. The most valuable cargo will be the one with the highest possible value to mass ratio. This leads us to the first and most obvious currency of the stars: information. But not just any information. We're talking about unique, irreplaceable, and densely packed knowledge. Imagine a starship arriving from a civilization orbiting a star 100 light-years away. Its most prized possession wouldn't be bars of gold or rare minerals. It would be a data crystal containing the complete scientific and cultural archives of its home world. This could include the solution to a fundamental physics problem that has stumped scientists for generations, the complete genetic library of an entire planet's biosphere, or the accumulated artistic and historical records of 1,000 years of peaceful development. This kind of knowledge has transformative power. A single breakthrough in energy generation or material science, purchased from a distant star, could revolutionize an entire civilization, paying for the cost of the voyage 1,000 times over. The trade becomes less about acquiring a product and more about acquiring potential. Beyond pure data, there is the trade in unique physical artifacts, but of a very specific kind. Consider materials that can only be formed under extreme conditions impossible to replicate artificially. A fragment of a neutron star with its hyper-dense matter could be a laboratory in a box for physicists. Exotic elements forged in the heart of a supernova might have properties that enable technologies we can't even conceive of. Then there are biological treasures. A seed bank containing the flora of an alien world, perfectly preserved, could offer new medicines, new food sources, or simply profound scientific insight. These are not bulk goods, they are singular specimens, their value derived from their uniqueness and their origin. They are the cosmic equivalent of a rare diamond or a priceless painting, but with the added value of potentially holding the key to a technological or biological revolution. This redefinition of wealth naturally leads to new forms of economic activity. The most important corporations in this future might not be mining or manufacturing conglomerates, but intellectual property firms, research collectives, and cultural archives. Their assets are patents, genetic codes, and artistic licenses valued across light years. We could see the emergence of knowledge futures, where colonies invest in scientific missions to distant stars with the expectation of a return on the data they might send back a century later. The entire economic model would have to adapt to timescales that dwarf human lifetimes. Contracts would be written not for years, but for centuries, with clauses that account for the time dilation experienced by the AI pilots and the potential for entire political systems to rise and fall during the transaction. Trust and long-term reputation would become the bedrock of commerce, as the delay in communication makes real-time negotiation and enforcement impossible. In this light, the magnetic corridors themselves take on a new character. They are not like the railroads of the 19th century, carrying coal and steel to fuel an industrial revolution. They are far more analogous to the first transatlantic telegraph cables, which suddenly allowed ideas and news to cross the ocean in minutes instead of weeks. The corridors are ultra-high bandwidth data pipelines, but with a twist, the data is physically carried on ships. Why send a physical ship when you could just beam the information at the speed of light? The answer lies in security, volume, and uniqueness. A laser beam carrying data can be intercepted, degraded over distance, or simply lost. A physical ship carrying a solid-state data vault, protected by layers of shielding and the vastness of space, is an incredibly secure way to transfer a civilization's most valuable secrets. Furthermore, the amount of data that could be stored on a ship is virtually limitless compared to the bandwidth of an interstellar laser link. And finally, the ship can carry unique physical objects that have no digital equivalent. The corridors enable the transfer of both perfect copies and priceless originals. Ultimately, this economy of ideas transforms the very purpose of expansion. It shifts the motivation from territorial conquest and resource extraction to cultural and intellectual exchange. A colony's success would be measured not by the size of its territory or the output of its factories, but by the richness of its knowledge base and its reputation as a reliable trading partner. Wealth becomes less about material accumulation and more about cognitive diversity. The greatest treasure a world could possess would be a vast interstellar library, constantly updated by ships arriving from 100 different stars, each bringing new perspectives, new art, and new discoveries. This flow of ideas would prevent the stagnation of isolated human cultures, fostering a galactic renaissance where innovation is fueled by the cross-pollination of knowledge from across the cosmos. The magnetic corridors, therefore, become the arteries of a truly enlightened civilization, carrying not ore, but the very essence of progress itself. The most immediate and profound change would be the complete redefinition of community. For the first time in history, a human colony established around a distant star would not be a one-way trip into permanent isolation. It would be more like founding a new city on a far-off continent, connected to the home world by a reliable, if slow, communication and supply line. These colonies would transform from lonely outposts into interconnected nodes within a vast, slow-moving network. Imagine a future where a political decision made on Earth takes 50 years to reach a colony orbiting Tau Ceti, and another 50 years for their response to return. This creates a form of dialogue that unfolds over centuries, forcing a radical shift in how societies think about governance, law, and collective identity. It would be less like a real-time conversation and more like the exchange of deeply considered letters between pen pals separated by an ocean, where each message carries the weight of generations. This glacial pace of cultural exchange would, paradoxically, lead to an explosion of human diversity unlike anything we have ever witnessed. Isolated for decades or even centuries between physical visits from trade ships, each colony would inevitably develop its own unique customs, art forms, social norms, and even dialect. They would adapt to their specific planetary environments, their cultures shaped by the light of their sun, the geology of their world, and the unique challenges they faced. Then, when a trade ship finally arrives, it doesn't just bring cargo, it brings a time capsule from another branch of humanity. It delivers a century's worth of another world's music, literature, philosophical debates, and technological innovations. This would not be a rapid, homogenizing globalization, but a slow, deliberate process of cross-pollination. The result wouldn't be a single, bland galactic culture, but a vibrant tapestry of wildly varied human experiences, all contributing to a richer, more complex whole. The very concept of what it means to be human would expand to encompass these galactic variations. This new connectivity would also forge a novel form of political and economic power, derived not from controlling territory on a planet, but from controlling the pathways between stars. The most strategically valuable real estate in the galaxy would not be a resource-rich planet, but a key junction where multiple magnetic corridors intersect. The civilization that controls such a hub would effectively hold the keys to interstellar commerce, able to regulate traffic, levy tariffs, or even block passage. This gives rise to a new geopolitical landscape based on astrography, the layout of the star lanes. Alliances would form between systems connected by fast, stable corridors, creating spheres of influence that span light years. Conflicts might not be fought with fleets of warships, but through economic pressure, corridor blockades, or cyber attacks on the AI pilots navigating these routes. The classic struggle for resources would be replaced by a struggle for connectivity itself. Perhaps one of the most significant long-term effects would be the prevention of humanity's speciation. Without any contact, colonies separated by thousands of generations would inevitably evolve along different biological and cultural paths, eventually becoming separate species, unable to interbreed and possibly even to communicate. The establishment of trade routes, even slow ones, acts as a gentle thread of genetic and mimetic exchange that binds the human family together. While each colony would diversify, the occasional arrival of new people and ideas would ensure that we remain a single, albeit incredibly varied, species. This fosters a truly galactic identity. A person born on a world-orbiting Barnard star would still think of themselves as part of a larger human civilization, with a shared history pointing back to Earth and a shared future intertwined with countless other worlds. Our planet would gradually shift from being the center of humanity to being its birthplace, a revered province in a much larger realm, much like ancient Athens is viewed within modern Greece, a foundational origin point, but no longer the sole seat of power or culture. This slow-motion society would fundamentally alter our perception of time and legacy. Projects would be planned not for electoral cycles or corporate quarterly reports, but for centuries. A family might plant a grove of trees knowing that their great-great-grandchildren will harvest the wood to build a ship that their descendants will launch. Art would be created with the understanding that its true audience might not experience it for 100 years. This long-term perspective could cultivate a deeper sense of responsibility and patience, qualities often in short supply in our fast-paced world. The establishment of interstellar trade would do more than just move goods. It would rewire the human psyche, encouraging us to think in terms of lineages and epochs, finally aligning our ambitions with the vast, patient timescales of the cosmos we aim to call home. To truly grasp how this grand vision could transition from theory to reality, let's focus our attention on the most logical starting point, a tangible case study, the very first magnetic corridor connecting our own solar system to our nearest stellar neighbor, Alpha Centauri. This project would become the proving ground, the interstellar equivalent of the Wright brothers' first flight at Kitty Hawk, a demonstration that would change humanity's future forever. The initial phase would be one of intense and meticulous observation. Before a single stabilizer is built, we would need an exquisitely detailed map of the magnetic landscape in our local interstellar neighborhood. This task would fall to a new generation of space telescopes, perhaps stationed at the gravitational balance point beyond Pluto, their instruments tuned not to the light of stars, but to the faint radio whispers of charged particles tracing magnetic field lines. Their mission would be to find the celestial river, a stable, coherent flow of magnetic force connecting our Sun to the Alpha Centauri system. The goal would be to identify the smoothest and most direct pathway. This is not a simple straight line through space. Just as a river meanders around hills and through valleys, a magnetic corridor would likely follow a curved path, shaped by the gravitational pull of nearby stars and the subtle pressure of the galactic wind. Astronomers would be searching for a magnetic filament that is both strong enough to be useful and laminar, meaning its flow is smooth and predictable, avoiding regions known for turbulence, such as the turbulent aftermath of ancient supernovae or the chaotic magnetic fields surrounding rogue planets. This map would become the master blueprint, the foundational document upon which all subsequent engineering would depend. It would reveal the precise coordinates where the first robotic pioneers must be sent. Once the optimal route is charted, the construction phase would begin, an endeavor of almost unimaginable patience. The first mission would not be a crude ship, but a fleet of highly advanced, fully autonomous robotic probes. Their destination would not be Alpha Centauri itself, but strategic points along the mapped corridor, perhaps 1/10 or 1/4 of the way there. These probes would be the seeds from which the corridor grows, carrying the components for the first field stabilizers. Upon arrival at their designated posts, these robots would unfold like intricate origami, deploying vast solar panels to capture the feeble light of the distant sun and extending superconducting loops kilometers across. Their purpose would be to generate a localized, powerful magnetic field, acting as a beacon and a reinforcement for the natural pathway. Deploying these first stabilizers would be the most critical and nerve-wracking part of the entire project, a test of our robotic capabilities in the deep void. After the beacons are in place and their functionality confirmed, a process that could take decades due to the light-speed delay in communications, the stage would be set for the main event, the launch of the first mag-sail freighter. This vessel, likely named something hopeful like Starblazer or Pathfinder 1, would be a sight to behold. Its central habitat and cargo module would be dwarfed by the immense, diaphanous hoop of its magnetic sail, a shimmering circle of superconducting tape that glows faintly with contained energy. Its cargo would be carefully chosen for this historic proof of concept mission. It wouldn't carry industrial machinery or colonists. Instead, its holds would be filled with symbolic and scientific treasures, solid-state data crystals containing the entirety of human knowledge, art, and DNA records, scientific instruments designed to study the Alpha Centauri system upon arrival, and perhaps even simple, robotic landers for the potentially habitable planet Proxima Centauri b. The launch itself would be unlike any rocket launch we know today. There would be no violent, fiery ascent. Instead, the freighter would be gently towed by a reusable interplanetary tug out to the edge of our solar system, beyond the influence of the sun's magnetic bubble. There, at the very threshold of interstellar space, the magsail would be fully deployed. With a surge of power from its onboard reactor, the sail would generate its magnetic bubble, and the ship would slowly, gracefully, begin to feel the pull of the magnetic corridor. The acceleration would be infinitesimally small at first, barely perceptible, but it would be constant. Day after day, year after year, the ship would gain speed, silently surfing the magnetic waves toward its destination. The journey of this first freighter would be the longest waiting game in human history. For over a century, the people of Earth and the fledgling colonies of the solar system would track its progress. Its AI pilot would send back regular status reports, a faint signal telling us that all is well, that the ship is holding its course. Generations would be born, live their lives, and pass away during this voyage. The mission would become a background constant of human civilization, a testament to our species' capacity for long-term thinking. Then, after more than 100 years of silence, a new signal would be received. It would be weak at first, but unmistakable. It would be the message from the AI pilot announcing its successful arrival in the Alpha Centauri system, its magsail now reconfigured to use the star's own magnetic field as a brake. That single transmission, confirming that a vessel built by human hands had traversed the interstellar gulf and arrived intact, would mark a dividing line in history. It would prove that we are not forever chained to our sun, that the stars are within our reach. This first route, the Sol Centauri lane, would become the model, the template from which an entire network of galactic trade routes would eventually unfurl, connecting humanity into a single, star-spanning community. Of course, this vision of serene magnetic highways gliding between the stars presents an almost idyllic future. But we must temper that optimism with a sober assessment of the very real and formidable dangers that would lurk within this new frontier. The cosmos is not a gentle place. It is a realm of unimaginable violence and chaos, and any infrastructure we build within it would be constantly tested by forces beyond our current comprehension. The very magnetic fields we seek to harness can become sources of catastrophic failure. Consider the fury of a stellar flare. Our own sun occasionally unleashes these eruptions, but imagine a similar event from a young, hyperactive star situated near a crucial segment of a magnetic corridor. A stellar flare is not just a burst of light, it's an immense ejection of charged particles and a violent distortion of the star's magnetic field. This blast would race down the corridor at near light speed, a tsunami of electromagnetic energy that could overwhelm the field stabilizers, temporarily scrambling the magnetic pathway into an unpredictable maelstrom. A ship caught in such an event might find its magsail suddenly and violently repelled, like a leaf caught in a hurricane, potentially tearing the vessel apart or hurling it off course into the endless night. The scale of danger escalates even further with events like supernova shockwaves. When a massive star ends its life in a cataclysmic explosion, it doesn't just vanish. It sends a sphere of destructive energy and material rushing outward at a significant fraction of light speed. This shockwave carries with it its own powerful and chaotic magnetic field. If such an event occurred within a few dozen light years of a magnetic corridor, the consequences would be dire. The arriving shockwave would not simply disrupt the corridor, it could erase it entirely, overwriting the carefully maintained magnetic pathway with a turbulent, radioactive froth that could persist for centuries. The stabilizer stations themselves, those lighthouses of the void, would be facing an existential threat. their delicate systems vulnerable to the intense radiation and physical impact of high-velocity debris. A ship traveling through a region recently swept by a supernova remnant might find the highway gone, replaced by a navigational nightmare that its AI pilot has no map for. Beyond these spectacular astronomical events, there are more subtle, insidious hazards. The galaxy is thought to be filled with rogue planets, worlds flung from their star systems by gravitational interactions, now drifting alone in the darkness. A close pass by such a dark, massive object could gravitationally warp the local space-time enough to pinch and distort the magnetic field lines of a corridor, creating a kind of cosmic pothole or a sudden, unexpected bend. Furthermore, the corridors could pass through regions of space with naturally occurring magnetic anomalies or areas of intense cosmic ray flux that could interfere with a ship's sensitive instrumentation and even pose a radiation hazard to any biological cargo or crew. The AI pilot's greatest challenge would be navigating these unpredictable and unmapped hazards, making real-time decisions with limited information, where a single miscalculation could mean the difference between staying on course and being lost forever. Then there are the dangers that arise not from nature but from ourselves. The moment a magnetic corridor becomes a valuable economic artery, it becomes a target. This introduces the chilling prospect of cosmic piracy and warfare on an interstellar scale. Unlike the pirates of old who boarded ships with cutlasses, future pirates might be sophisticated hackers aiming to take control of a ship's AI pilot, turning the vessel and its priceless cargo of data or unique artifacts into a ghost ship drifting toward a secret rendezvous. Alternatively, a hostile faction could deploy a specialized vessel to a critical junction point, one designed not to travel the corridor but to sabotage it. This blockade runner could generate a powerful, localized magnetic field pulse to deliberately create turbulence, effectively placing a roadblock on the interstellar highway. The economic damage from disrupting trade between stars for even a few decades would be an act of war more impactful than any planetary invasion, holding entire civilizations hostage by threatening their connectivity to the wider galaxy. This leads us to the most profound and unsettling risk of all, the fallibility of the systems we create. The entire enterprise hinges on the flawless operation of two things: the artificial intelligence pilots and the corridor infrastructure itself. We are contemplating AIs that must operate autonomously for centuries without error. But what if a programming flaw, an unforeseen logical paradox, or a corruption in its core software emerges after 100 years of smooth sailing? The AI could make a catastrophic error, misinterpreting sensor data or entering a failure state from which it cannot recover, dooming the ship to drift aimlessly. Similarly, the field stabilizers are machines, and all machines eventually fail. A cascading failure in one stabilizer could place unsustainable stress on the adjacent stations, potentially causing a segment of the corridor to collapse like a line of falling dominoes. A ship relying on that now vanishing pathway would be like a train whose tracks are being ripped up just behind it, left stranded in a region of space where the natural magnetic field is too weak to provide any meaningful propulsion. The sheer timescales involved make absolute reliability an almost impossible dream, demanding a level of engineering redundancy and fault tolerance that pushes the boundaries of what is conceivable. Acknowledging these dark possibilities is not a rejection of the vision, but a necessary step in building a future where interstellar travel is not just possible, but resilient, safe, and secure for all who would dare to sail the magnetic seas. While establishing trade routes within our own Milky Way galaxy is a monumental task, it represents only the first chapter in a story that could span the entire cosmos. The ultimate, breathtaking ambition of this concept lies in reaching beyond our galactic shores, to the other island universes that dot the observable universe. The most prominent target in our celestial neighborhood is, of course, the Andromeda Galaxy, a swirling collection of nearly 1 trillion stars on a slow-motion collision course with our own Milky Way. But here, the challenges we face within our galaxy are magnified to an almost incomprehensible degree. The distances involved are no longer measured in mere light years, but in millions of them. Andromeda floats approximately 2.5 million light-years away. To put that in perspective, a signal sent from Earth at the speed of light today would not arrive in the Andromeda Galaxy until around 2,500,000 years from now. This is the sheer, staggering scale of the intergalactic void. The fundamental physics, however, offers a faint glimmer of possibility. Magnetic fields do not stop at the edge of a galaxy. They are believed to extend faintly into the vast and seemingly empty intergalactic medium. These fields are unimaginably weak, perhaps billions of times weaker than the fields we would hope to harness within our own galaxy. They are like the faintest whisper of a breeze after the hurricane-force winds of a galactic magnetic highway. Yet, theoretically, they are there. The concept of an intergalactic corridor would hinge on our ability to detect these whisper-thin filaments of magnetic force that might, like cosmic spider silk, connect one galaxy to another. The engineering required to reinforce such a tenuous pathway would be godlike. The field stabilizers would need to be structures on an unprecedented scale, perhaps harnessing the energy of multiple stars just to generate a detectable magnetic bubble in that profound emptiness. This leads to the most profound requirement for such an endeavor: time. A journey from the Milky Way to Andromeda via a magnetic corridor would not take centuries, it would take millions of years. This timescale immediately forces us to reconsider the very nature of the civilization that would undertake such a project. It could not be a civilization as we know it, with its fleeting political cycles and cultural revolutions. It would need to be a truly stable, enduring intelligence, capable of maintaining a single, coherent purpose over geological epochs. This civilization would have to think in units of time, where the rise and fall of a star is a routine event, and the collision of entire galaxies is a foreseeable logistical challenge to be planned for. The builders of the first intergalactic stabilizer would be as distant in time from the project's completion as we are from the first Homo habilis shaping stone tools. The endeavor would be less a project and more a permanent pillar of that civilization's identity. What, then, would be the purpose of such a trade route? The economic rationale that applies within a galaxy breaks down across such immense gulfs. Sending physical goods would be pointless. The only conceivable cargo would be information, but even that is complicated by the time lag. A message sent to Andromeda would take 2.5 million years to arrive, and a response would take the same time to return. This is not a conversation, it is a time capsule on a cosmic scale. The value would lie in the exchange of entire archives of knowledge, the complete biological and cultural history of a galaxy, sent as a single, monumental transmission via physical ships carrying solidified data. The arrival of a ship from Andromeda would be like receiving a message from a completely separate tree of life and intelligence, offering insights and perspectives forged in an entirely different cosmic environment. The trade would be in the currency of ultimate discovery, the sharing of two entirely separate galactic histories. This vision ultimately transcends practical commerce and enters the realm of cosmic destiny. It speaks to a future where intelligence seeks not just to explore, but to permanently connect the universe. Creating a network linking island galaxies would be the greatest act of synthesis possible, a declaration that the cosmos, for all its vastness and emptiness, can be woven together into a coherent whole. It represents the final frontier of connectivity, where the very structure of the universe becomes the substrate for a network of shared consciousness and knowledge. This is no longer a human endeavor. It is a project for intelligence that has matured beyond a single planet, a single star, or even a single galaxy, thinking and building on a scale that matches the universe itself. This shift in our cosmic ambitions reflects a deeper transformation in the human spirit, a move away from the mindset of a conqueror and toward the patience of a gardener. For centuries, our stories of space have been tales of conquest. We dream of planting flags on new worlds, of claiming territories, of boldly going where no one has gone before in a burst of heroic individual effort. This narrative is powerful, but it is also inherently transient. It is about arriving, making a mark, and moving on. The magnetic corridor concept, however, paints a different picture. It is not about the solitary explorer crossing a desert. It is about communities building a permanent road through that desert so that everyone who follows can travel more easily. This is the difference between a pioneer blazing a temporary trail and a civilization constructing an interstate highway system. The goal is no longer just to reach the destination, but to forge a lasting, sustainable link between here and there. This philosophy of connection over conquest naturally leads to a different set of priorities. Stability and sustainability become paramount. When you are just visiting a place, you might not worry about the long-term consequences of your actions. But when you are building a home or a highway that will be used for millennia, you must think differently. Constructing a magnetic corridor demands an investment in materials and energy that only makes sense if the structure will endure. This forces us to consider the long-term health of the interstellar medium itself. We would need to ask questions no conqueror ever would. How do our stabilizers affect the flow of cosmic rays over astronomical timescales? Could reinforcing a magnetic pathway inadvertently alter star formation in a nearby nebula a million years from now? This perspective cultivates a sense of cosmic stewardship, where humanity acts as a careful custodian of the galactic environment, ensuring that our infrastructure integrates harmoniously rather than disrupts violently. The very nature of the travel facilitated by these corridors reinforces this patient, integrative approach. A magsail journey is not a frantic sprint. It is a gradual, graceful arc across the light years. There is no explosive launch, just a gentle, continuous acceleration. This slow, deliberate pace is a physical manifestation of the philosophical shift. It discourages a get-there-quick, grab-what-you-can mentality and encourages a long-term view. The societies that dispatch these ships are making investments that will not pay off for centuries. They are playing a game whose final moves they will never see, trusting in the judgment of AI pilots and the stability of infrastructure they built. This requires a profound faith in the future and a commitment to generations yet unborn, fostering a culture that values legacy and continuity over immediate gratification. Ultimately, this vision suggests a future where humanity seeks not to dominate the cosmos, but to become a woven thread within its grand tapestry. We would transition from being tourists in the galaxy to being permanent residents. Our structures, the field stabilizers, would become enduring features of the interstellar landscape, as permanent as any natural astronomical formation. Our trade routes would become the ligaments connecting a distributed, multi-stellar civilization. This changes our fundamental identity. We are no longer just the species from Earth. We become a galactic species with our history, our economy, and our culture spanning multiple star systems. Our fate becomes intertwined with the fate of the galaxy itself. This philosophical evolution from seeing the universe as a territory to be conquered to seeing it as a community to be joined may be the most critical breakthrough of all. For the technology to build magnetic corridors is one thing, but the wisdom to use them in a way that ensures our lasting, positive presence among the stars is what will truly define our success. This fundamental challenge of time is woven into the very fabric of the universe, dictated by the unchangeable speed of light. It means that every aspect of interstellar commerce must be rethought for an environment where instant communication is an impossible fantasy. Imagine a trading company on Earth wishing to purchase a unique data archive from a colony orbiting Barnard star nearly 6 light-years away. The initial inquiry, sent via a tight-beam laser signal, would take 6 years to arrive. The colony's administrators would then discuss the offer, a process that might take a year of their local time. Their reply, whether an acceptance or a counter-proposal, would then take another 6 years to travel back to Earth. A simple negotiation, one that today would be settled in an afternoon of emails, would stretch across 13 years. The entire concept of a market that reacts in real time to supply and demand completely evaporates across such distances. This forces the development of an economy built not on quick deals, but on long-term forecasts and, most importantly, unwavering trust. Transactions would be governed by incredibly detailed smart contracts, recorded on distributed ledgers that are synchronized across star systems with each ship's arrival. These contracts would have to account for every conceivable variable over a century or more. What if the company sending the goods goes bankrupt 50 years into the voyage? What if the receiving civilization undergoes a political revolution and renounces the debt? The legal framework would need clauses that activate based on verified, time-delayed news reports carried by other trade ships. Reputation would become the most valuable asset a trading house or a world could possess. A colony known for honoring contracts that were signed by their great-grandparents would be a far more desirable partner than one with a history of defaulting on ancient agreements. Commerce becomes a sacred promise made across generations. The strangeness deepens considerably when we factor in the effects of special relativity, a phenomenon known as time dilation. For the AI-piloted magsail ships traveling at a significant fraction of light speed, time itself does not pass at the same rate as it does for the stationary observers on planets. From the perspective of Earth, a voyage to Alpha Centauri might take 120 years, but for the clock on the ship, the journey might only take, say, 100 years. The ship and its contents have effectively traveled 20 years into the future relative to the civilization it left behind. Now, imagine if there were biological crews on these vessels, perhaps in suspended animation or living generational lives aboard the ship. They would experience the journey in that shorter, ship-based time frame. When they arrived at their destination, they would be 20 years younger than they would have been if they had stayed home. They would be true time travelers, arriving in a future that has aged more than they have. This creates a bizarre and complex sociological dynamic. Consider a family-run trading concern that sends its scion on a round-trip journey to a star 10 light-years away. From Earth's perspective, the trip takes 50 years out and 50 years back, a full century. But due to time dilation, the trader might only age 80 years. They would return to an Earth where their younger siblings are now older than they are, where their children are senior citizens, and where the world they knew is a distant memory. The very concept of a contemporary becomes fluid. The trader would be a living anachronism, a visitor from the past trying to reintegrate into a society that has moved on without them. This could lead to a unique class of interstellar merchants, individuals who are psychologically disconnected from any single era, forever out of sync with the rest of humanity. The economic implications are equally profound. The value of a cargo would be assessed not just at the time of departure or arrival, but with an understanding of the temporal distortion involved. A ship carrying cutting-edge technology might find that its goods are obsolete by the time it arrives, if the destination civilization has continued to innovate during the voyage. Conversely, a ship carrying timeless cultural artifacts or fundamental scientific data might actually increase in value over the journey. The most successful traders would need to be brilliant long-term futurists, able to predict technological and cultural trends not for a few years but for a century or more. They would be making bets on the direction of entire civilizations, placing wagers that would not be settled until long after their own natural lifespans had ended. The entire trade network, therefore, must be designed as a temporally fluid system, with buffers and adaptive protocols to handle these inevitable dislocations, ensuring that the flow of commerce can continue smoothly even when every participant is living in a slightly different present moment. But who would build and maintain these vast interstellar pathways, stretching across light years and operating for millennia? The answer cannot be human crews, for the sheer scale and time span of the corridor network demands a workforce of a different kind, a silent, self-sustaining army of robotic engineers. These would not be the robots of today's factories. They would be autonomous systems of incredible sophistication, capable of construction, maintenance, and even self-replication in the deep void. Their mission would be to act as the permanent, unseen stewards of the galactic infrastructure, a mechanical ecology working tirelessly to keep the trade routes open. The reliability of this robotic workforce becomes the single most critical factor for the entire interstellar economy, for a single, undetected design flaw could cascade into a corridor's failure over centuries, stranding ships and isolating entire civilizations. The future of galactic commerce would literally rest on the robust, fault-tolerant shoulders of our mechanical progeny. The life cycle of this endeavor would begin with a single, advanced seed factory. Imagine a spacecraft, perhaps no larger than a modern-day satellite, dispatched from our solar system towards a resource-rich asteroid belt in a nearby star system. This seed factory would be a marvel of miniaturization and versatility, carrying the core blueprints and a minimal set of universal tools. Upon arrival, its first task would be the most fundamental: survival and replication. It would land on a metal-rich asteroid and begin the painstaking process of using local materials: ice for water, rocks for minerals, and metals for structures, to build a copy of itself. This is the principle of self-replication, a concept sometimes called von Neumann probes. The original seed factory would not build a corridor stabilizer first, it would build another factory. Then those two would build two more, and so on, creating an exponentially growing workforce capable of tackling the monumental construction project that lies ahead. Once a critical mass of these robotic units is established, they would shift their focus to the primary task: constructing the field stabilizers that define the magnetic corridor. This would be a coordinated effort of breathtaking complexity. Some robots would function as miners, tirelessly extracting resources from asteroids. Others would be transports, moving raw materials to designated construction sites in the empty space between stars. A third group would be the assemblers, using advanced manufacturing techniques like 3D printing in the vacuum of space to fabricate the massive superconducting coils and power systems of the stabilizers. There would be no central command from Earth. Instructions would have been embedded in their original programming, and they would communicate with each other in a distributed network, making collective decisions about resource allocation, construction schedules, and problem solving. They would form a true hive mind, an industrial ecosystem operating with a single, unified purpose across astronomical distances. The challenge of maintenance is even more daunting than construction. These stabilizers, exposed to the harsh environment of space for millennia, will inevitably degrade, Cosmic radiation can damage electronics, micrometeoroid impacts can cause physical harm, and the sheer passage of time can lead to material fatigue. The robotic network must therefore be a permanent feature, a self-sustaining maintenance core. They would conduct endless patrols along the corridor, their sensors constantly scanning each stabilizer for signs of wear. Upon detecting a fault, a team of specialized repair bots would be dispatched. They might need to replace a damaged solar panel, patch a breach in a coolant line, or even perform delicate surgery on the stabilizer's complex computer brain. All of this would be done autonomously, using spare parts manufactured from harvested space resources. The corridor must be able to heal itself without any hope of outside intervention. This leads to the most critical requirement, absolute reliability. We are not talking about a machine that needs to work for a decade. We are talking about systems that must function flawlessly for timescales longer than human history. A single programming error, a subtle flaw in a material's composition, or a vulnerability in the swarm's communication protocol could have catastrophic consequences. Imagine a bug that causes a repair robot to misinterpret sensor data, leading it to fix a perfectly functional stabilizer by accidentally disabling its magnetic field. This error might go unnoticed for years until a trade ship relying on that section of the corridor finds the pathway weakened and is thrown off course. Over centuries, such small errors could compound, leading to the slow, silent degradation of the entire network. Therefore, the AI governing these machines must be beyond robust. It must be inherently fail-safe, with layers of redundant systems and a conservative decision-making logic that prioritizes the long-term health of the corridor above all else. The creation of this flawless robotic ecology is perhaps the greatest engineering challenge in the entire vision, demanding a level of foresight and quality control that borders on perfection. This brings us to a profound and often overlooked dimension of this entire endeavor: the environmental impact. When we talk about building on Earth, we conduct environmental impact studies to understand how a new highway might affect a local watershed or a species migration pattern. But what is our responsibility when the environment we are altering is the galaxy itself? The interstellar medium, that vast expanse of thinly spread gas and dust between the stars, might appear to be a total void to our eyes, but it is a dynamic and complex ecosystem on a cosmic scale. It is the raw material from which new stars and planets are born. By embarking on a project to reshape its magnetic architecture, we are not just building in empty space. We are intervening in a natural system that has been evolving for billions of years. The question we must confront is not just can we do this, but should we? The potential for unintended consequences is staggering. Consider the process of star formation. Stars are born within colossal clouds of molecular gas and dust, and the prevailing scientific understanding suggests that magnetic fields play a crucial role in this delicate cosmic dance. These fields provide a supportive framework, helping to counteract the force of gravity long enough for the cloud to fragment and collapse into protostars. Now, imagine we reinforce a magnetic corridor that passes near one of these stellar nurseries. Could our artificial strengthening of the field lines inadvertently trigger a premature collapse, causing a burst of star formation? Or conversely, could it provide too much support, effectively putting a star-forming region into a state of suspended animation, preventing new suns from igniting? We are like a child tinkering with the dials of a machine we do not fully understand. A small adjustment in one place could have cascading effects millions of years later across an entire sector of the galaxy. Another critical function of the interstellar medium is its role in regulating cosmic rays. These are high-energy particles, mostly protons and atomic nuclei, that race through space at nearly the speed of light. They are thought to be accelerated by shock waves from supernovae, and their journey across the galaxy is heavily influenced by magnetic fields, which bend their paths and effectively contain them. The galactic magnetic field acts as a kind of cosmic sponge, trapping and diffusing these rays. If we were to create large-scale, reinforced magnetic corridors, we might be inadvertently creating channels that funnel cosmic rays, or barriers that block their natural dispersal. This could have implications we cannot yet foresee. Cosmic rays are believed to play a role in atmospheric chemistry on planets, and may even influence mutation rates in biology. Altering their galactic distribution could have subtle but profound effects on the potential for life elsewhere, a responsibility of almost unimaginable gravity. This forces the development of an entirely new philosophical and legal framework, interstellar environmental ethics. We would need to move beyond a mindset of exploitation and embrace one of cosmic stewardship. This would involve establishing principles for a galactic leave-no-trace policy. Before deploying a field stabilizer, we would need to conduct long-term astronomical observations to ensure we are not building in a sensitive astro-ecological zone, like the vicinity of a protoplanetary disk or a unique nebula. We might need to create protected areas analogous to national parks on Earth, where no magnetic infrastructure is permitted in order to preserve pristine conditions for scientific study, or simply out of respect for the natural order. This is a profound shift in consciousness, acknowledging that humanity has a responsibility not just to its own future, but to the well-being of the galactic environment it now inhabits. The challenge is that we are the first species on the block, as far as we know, capable of such large-scale engineering. There is no precedent, no existing galactic treaty to guide us. We would be writing the rulebook from scratch. This would require a collaboration not just between nations, but between scientific disciplines. Ethicists, astrophysicists, ecologists, and philosophers would need to work together to define what constitutes harm in an interstellar context. What is our duty to potential life that might exist on planets we have never seen? What is our obligation to future generations of humans or other intelligent species to preserve the natural galaxy? These are not scientific questions with easy answers. They are deep, ethical dilemmas that strike at the heart of what it means to be a civilized species venturing into a vast and largely untouched wilderness. Building magnetic corridors is not just an engineering project. It is a test of our collective maturity, a measure of whether we can wield cosmic power with wisdom and humility. The grand vision of intergalactic magnetic highways can feel like a distant dream, but the fascinating truth is that the first, crucial steps are being taken right now, in laboratories and research centers around the world. We are not staring at a blank slate, we are actively assembling the foundational toolkit. This isn't about building a starship tomorrow, but about solving 1,000 smaller puzzles that, when combined, will make the impossible seem inevitable. The journey begins with a deep and growing mastery over the fundamental forces we intend to harness, starting with the quest for perfect conductivity. The development of new superconducting materials is arguably the most critical near-term technology. A magnetic sail, the heart of our future starship, relies on a massive loop of wire that can carry an immense electrical current indefinitely without any loss of energy to resistance. Today's best superconductors require incredibly cold temperatures, often using expensive and cumbersome liquid helium cooling systems. But breakthroughs in high-temperature superconductors, materials that exhibit this magical property at less extreme, more manageable temperatures, are happening regularly. Each new compound that pushes the temperature threshold higher brings us closer to the day when we can envision constructing a lightweight, powerful magsail that can operate reliably in the deep freeze of space without an impossibly complex and heavy cooling apparatus. This is a quiet revolution in material science, but it is the very bedrock upon which the entire concept of magnetic propulsion rests. Parallel to this, our understanding of plasma physics is being refined in some of the most energetic experiments on Earth. While we talk about harnessing the plasma winds of space, we are already learning to create and control miniature stars in laboratories through nuclear fusion research. Projects like the International Thermonuclear Experimental Reactor, or ITER, are monumental endeavors not just for energy production, but for our comprehension of how superheated plasma behaves within powerful magnetic fields. The donut-shaped tokamak reactors used in these experiments are essentially containers made of magnetic force, designed to hold plasma at temperatures of over 100 million degrees Celsius. The knowledge gained from keeping this chaotic, energetic substance stable is directly applicable to understanding how to navigate the more diffuse, but equally unpredictable, plasma flows along a galactic magnetic corridor. Every time a physicist models a plasma instability or designs a more efficient magnetic coil for a fusion reactor, they are inadvertently writing a textbook for future interstellar navigators. And we are not just thinking about these technologies in the abstract, we are already testing their principles in the void. The venerable Voyager probes, launched in the 1970s, have become our first robotic pioneers into the magnetic landscape of interstellar space. As they passed beyond the influence of the Sun's magnetic bubble, their instruments recorded a dramatic shift, providing humanity with its first direct measurements of the magnetic field of the galaxy itself. While their data is a single, narrow thread, it confirmed that these fields exist and can be mapped. Now, newer missions are taking up the torch. The upcoming Interstellar Mapping and Acceleration Probe, or IMAP mission, scheduled for launch in the coming years, is designed specifically to study the interaction between the solar wind and the interstellar medium. It will create the most detailed map yet of the boundaries of our solar system, a crucial first chart of our local cosmic neighborhood. This is the very essence of galactic magnetography, starting small, right on our cosmic doorstep. Perhaps the most exciting near-term precursor is the active research into solar sails and their more advanced cousin, the magnetic sail, for propulsion within our own solar system. The successful JAXI-CAROS mission and the Planetary Society's Light Sail 2 have brilliantly demonstrated that sailing on light pressure from the Sun is a viable and elegant means of propulsion. The logical next step is to scale this up to a magnetic sail or magsail, which could be used for efficient travel between planets without propellant. Concepts are already being drawn up for magsails that could use a small loop to generate a magnetic field, interacting with the solar wind to slowly but constantly accelerate a probe toward the outer planets. A successful demonstration of a magsail operating between Earth and Mars, for instance, would be a paradigm-shifting event. It would prove that the core technology works, transforming the concept from a theoretical equation in a physics paper into a practical engine that has flown in space. Each such mission would be a stepping stone, building confidence and technological maturity on progressively longer journeys, first to the asteroid belt, then to Jupiter, and finally, to the edge of the solar system where the true interstellar winds begin. Underpinning all of this physical infrastructure is the silent, rapid evolution of artificial intelligence and autonomous robotics. The future corridor network will be built and maintained not by astronauts in spacesuits, but by intelligent machines capable of independent decision-making over decades. The Mars rovers, with their increasing levels of autonomy, are our first glimpse of this future. They can already navigate terrain, select scientific targets, and perform basic troubleshooting on their own, a necessity when a command from Earth can take 20 minutes to arrive. The next generation of robots will be far more independent, capable of complex construction tasks in orbit or on the Moon. The development of these systems is not happening for interstellar travel specifically. It is being driven by our immediate goals in space exploration and terrestrial industry. But every time a self-driving car navigates a complex intersection or a robotic arm assembles a satellite in orbit, we are refining the very same sensor fusion, pattern recognition, and decision-making algorithms that will one day allow a robotic constructor to build a field stabilizer around a distant star entirely on its own. The path to the stars is not a single, giant leap, but a mosaic of 10,000 smaller advances, each one taking place in a university lab, a corporate research park, or a mission control center, slowly and steadily turning science fiction into tomorrow's engineering reality. Of course, such a grand vision invites equally grand skepticism, and it is absolutely essential that we listen to these critical voices, for they are not adversaries of progress but its essential guides. The most immediate and formidable objection centers on energy. Critics rightly point out that the power required to generate and sustain magnetic fields across light years of space is so colossal it may violate fundamental laws of thermodynamics as we understand them. Proposing to harness the output of entire stars through Dyson swarms feels, to many, like a leap from engineering into mythology. It's a fair point. We are essentially suggesting that a future civilization would command energy on a scale that rivals natural astrophysical processes. The counter-argument isn't a denial of this immense challenge, but rather a perspective on technological evolution. Every major leap in human capability has been preceded by a leap in energy mastery. The Industrial Revolution required coal, the 20th century ran on oil, and the Information Age is powered by electricity. The transition to a Type II civilization on the Kardashev scale, one that harnesses the power of its star, is the logical, if staggering, next step. The energy requirement isn't a proof of impossibility. It is the precise definition of the barrier we must eventually cross to become an interstellar species. The magnetic corridor concept doesn't create this energy problem. It simply inherits it from the broader ambition of interstellar travel itself. Another profound criticism focuses on the element of time. The timelines involved centuries for construction. Millennia for travel between galaxies are so vast they seem to defy any notion of a stable, continuous civilization. Human history is a story of empires rising and falling, of knowledge being lost and rediscovered. Could any society possibly maintain the focus and resources for a project whose completion lies hundreds of generations in the future? This skepticism strikes at the heart of our cultural and psychological limitations. The counterpoint here involves a necessary evolution in our thinking. A civilization capable of such projects would not be like our own. Its institutions, its methods of record-keeping, and its very sense of identity would have to be engineered for longevity. It might rely on artificial intelligences as the guardians of long-term goals, entities for whom 1,000 years is a manageable planning cycle. Furthermore, the project itself could become the central pillar of that civilization's identity, a cultural touchstone that provides meaning and direction across millennia, much like the building of great cathedrals did in the Middle Ages, but on a cosmic scale. The challenge is not the timescale itself, but our ability to grow into a species that can think on such timescales. Then there is the practical physics of the interstellar medium itself. Skeptics argue that galactic magnetic fields are simply too weak and too turbulent to be of any practical use. They are not like the smooth, powerful fields we generate in a laboratory. They are a chaotic tapestry, twisted by supernova explosions, distorted by dark matter, and varying wildly in strength. Trying to ride such a field might be like trying to sail a paper boat on a stormy ocean. This is perhaps the most technically grounded criticism. The response isn't to dismiss the turbulence, but to incorporate it into the design. The concept doesn't require that we use the magnetic fields exactly as we find them. The entire purpose of the field stabilizers is to act as active regulators, to smooth out the turbulence and reinforce the weak spots. It's the difference between trying to drive a cart down a muddy, rutted path and paving a highway. The natural magnetic field provides the initial, faint trail, but the engineering creates the reliable roadway. This acknowledges the criticism while proposing a solution that turns a weakness into a manageable variable. Perhaps the most compelling counter-argument is that magnetic corridors, even if feasible, might represent an intermediate technology, eventually made obsolete by something more revolutionary. What if the real future of interstellar travel lies not in crossing space, but in bypassing it altogether through theoretical constructs like wormholes or warp drives? If we could fold space-time or create a shortcut between 2 points, the arduous journey along a magnetic highway would seem quaint and inefficient. This is a healthy dose of humility. It forces us to admit that our vision is constrained by our current understanding of physics. The relationship between these technologies might not be one of replacement, but of synergy. Magnetic corridors could be the reliable, slow boat method for establishing initial contact and building infrastructure, a proof of concept for an interstellar economy. The discovery of a wormhole stabilization technique could then build upon that existing network, creating a tiered transportation system with magnetic routes serving as local access roads to wormhole expressways. Skepticism about the ultimate solution encourages a flexible, multi-path approach to research. Ultimately, this dialogue between ambitious vision and rigorous criticism is not a barrier to progress. It is the very engine of scientific discovery. Every great leap forward, from the theory of plate tectonics to the development of quantum mechanics, was initially met with deep and valid skepticism. That skepticism forced the pioneers to sharpen their arguments, refine their models, and seek better evidence. Engaging seriously with the critics of magnetic corridors does not weaken the idea. It strengthens it by identifying the precise areas where our knowledge is most lacking. It tells us to focus our research on high-temperature superconductivity, on detailed mapping of the interstellar magnetic field, and on the development of truly autonomous AI. This process transforms a captivating science fiction premise into a serious, if long-term, scientific and engineering roadmap. The goal is not to prove the skeptics wrong, but to work with them to identify which obstacles are truly insurmountable walls and which are simply mountains waiting to be climbed. This grand vision of magnetic highways stitching the galaxy together is not an isolated invention destined to rise alone. It is far more like a single instrument in a future symphony of technology, where each breakthrough amplifies and enables the others. To see magnetic corridors as the sole solution is to miss the bigger picture of a truly interconnected interstellar civilization. Their true power is unlocked when they work in concert with other revolutionary technologies, each solving a piece of the immense puzzle of spanning the light years. This symbiotic relationship transforms a clever idea into a viable, living infrastructure. The corridor enables the physical connection, but it is the other technologies that will breathe life into that connection, making it meaningful and manageable for the civilizations that use it. Consider first the agonizing problem of communication delay. A ship might take a century to travel a magnetic corridor to a neighboring star, but even a simple message sent by radio or laser would still take years to make the same journey at the speed of light. This creates a profound isolation where colonies are effectively cut off from real-time dialogue. This is where a technology like quantum entanglement could change everything. While often simplified in popular science, the theoretical potential of quantum communication is to create a link between two particles that is instantaneous, regardless of distance. If such a technology could be perfected and scaled, it would not speed up physical travel, but it would utterly eliminate the lag for data. Imagine a future where the AI pilot of a ship halfway to Alpha Centauri can send an instantaneous status report to mission control on Earth. Colonists could have a live video call with their families back home, even though they are separated by trillions of miles. This transforms the nature of the journey from one of absolute solitude to one of continuous connectivity. The magnetic corridor carries the physical body of the ship, while the quantum link carries its voice and spirit, ensuring that no traveler is ever truly alone. Then there is the biological challenge of the human lifespan. Even with the gentle, continuous acceleration of a magsail, a journey to a nearby star will likely span multiple human generations. This raises profound questions about the purpose of sending people, as the original crew would perish long before reaching their destination. Here, advances in biological science offer parallel pathways. One avenue is advanced cryogenic stasis, the concept of suspending biological functions entirely for the duration of the voyage. This isn't the frozen sleep of science fiction cliché, but a sophisticated process of vitrification, where the body's water is replaced with protective chemicals to prevent ice crystal formation, allowing the individual to be preserved in a state of suspended animation. Upon arrival, they would be revived, having subjectively experienced only the launch and the landing. Another, even more radical possibility is mind uploading, where the complete neural structure of a consciousness is mapped and transferred to a durable computational substrate. The physical body would be left behind, and the individual's consciousness would travel as data, perhaps even being transmitted ahead of the ship via that quantum link, to be reinstantiated in a synthetic or cloned body upon arrival. In this scenario, the magnetic corridor is transporting a valuable physical archive or a colony seed ship, while the colonists themselves arrive by other means, their journey measured in minutes, not centuries. This interconnectedness extends to the very fabric of the corridors themselves. The field stabilizers we've discussed, those lighthouses of the void, will not be simple magnets. They will be incredibly sophisticated computational nodes, powered by artificial intelligence that far surpasses our current understanding. This AI won't just manage the magnetic field. It will need to predict solar weather from nearby stars, navigate around cosmic debris, and communicate with a flowing river of ships, all while performing self-diagnosis and repair. The development of such robust, autonomous intelligence is a technology field in its own right, one that is deeply symbiotic with the corridor infrastructure. You cannot have one without the other. The AI is the brain of the corridor, and the magnetic field is its body. Progress in machine learning and cognitive computing directly enables the safe and efficient operation of the transportation network. Even the construction of the corridors is a symbiotic process. We mentioned self-replicating robots, but their effectiveness hinges on advancements in situ resource utilization, or ISRU. This is the technology of living off the land in space. These robotic builders will need to identify suitable asteroids, extract metals and water ice, and process them into usable components like superconducting wire and structural alloys, all without any supply chain from Earth. Breakthroughs in autonomous chemistry and advanced manufacturing are prerequisites for the corridor network to build itself. The development of ISRU for a lunar base or a Mars colony is a direct stepping stone to the technology needed to build field stabilizers around another star. Each piece of the puzzle fits together. The future of interstellar civilization is not a single, shiny invention that solves everything. It is a convergent web of innovations, where a breakthrough in quantum physics here enables a leap in communication there, which in turn makes a biological solution viable, which then justifies the engineering investment in the physical transportation system. The magnetic corridor is the backbone, but it is the synergy of all these other technologies that creates the nervous system, the circulatory system, and the very consciousness of a galaxy-spanning society. But these magnificent corridors are more than just feats of engineering. They are also potential sources of conflict. The moment a magnetic pathway becomes a vital economic artery, the question of ownership and regulation becomes paramount. Who exactly has the right to control a river of magnetic force that flows through the void between stars? Is it the civilization that first mapped and reinforced it? Is it the star systems at either end? Or does it belong to all of humanity as a common good, a cosmic commons? This is not an abstract philosophical debate. It is the foundational challenge of establishing a legal and governance framework for an interstellar civilization, a system we might call the Lex Galactica. Our terrestrial legal systems, built on the assumption of quick communication and swift enforcement, would be utterly useless when a legal summons takes 50 years to deliver and a court's ruling arrives a century after the dispute began. We would need to build a system of justice that operates as patiently as the ships that sail these routes. The most immediate and complex issue revolves around contracts and commerce. Imagine a company based in the Sirius system agrees to deliver a cargo of advanced medical data to a colony orbiting Procyon. The journey will take 120 years. How do you write a contract for that? It must account for possibilities that span generations. What if the company goes bankrupt 70 years into the voyage? What if the receiving colony undergoes a political revolution and renounces the debt upon the ship's arrival? The contract would need to be a self-executing, incredibly detailed document, likely encoded as a smart contract on a distributed ledger that is synchronized across star systems. Each trade ship would carry an updated copy of this galactic blockchain, and every stabilizer station along the route would act as a validating node. The contract could have clauses that automatically release payment to the ship's owners upon verification of its departure, with further payments triggered when it passes certain checkpoints, all managed by the autonomous system without the need for slow, light-speed lawyers. Dispute resolution would require an equally radical innovation. There can be no interstellar police force ready to board a ship light years from home. Instead, enforcement would have to be economic and reputational. A civilization or corporation that consistently violates agreements would find itself blacklisted. Its ships might be denied access to corridor stabilizers, effectively stranding them. Its financial transactions could be rejected by the galactic ledger. In this slow-motion economy, a reputation for honesty and reliability would become the most valuable currency, more important than any material wealth. A specialized, decentralized court system might evolve, perhaps composed of respected AIs or panels of jurists from neutral star systems. Their rulings would not be enforced by guns, but by the collective consensus of the network, a form of peer pressure on a galactic scale where isolation is the ultimate penalty. Then there is the critical matter of corridor traffic management and safety. These are not empty highways. They would be bustling with ships traveling at significant fractions of light speed. Without careful coordination, a collision would be catastrophic. This necessitates a universal set of navigation rules, a galactic equivalent of maritime law or air traffic control. The AI pilots of the ships would need to communicate with each other and with the corridor's management system to maintain safe distances and coordinate maneuvers. Right-of-way protocols would need to be established. Is a ship leaving a corridor required to yield to one entering? What are the procedures for a ship in distress? The field stabilizer stations would serve as the traffic control centers, constantly broadcasting navigation hazards and managing the flow of vessels to prevent cosmic gridlock. This system would have to be flawless, as a single error could lead to a disaster that wouldn't be discovered for decades. The ultimate challenge is one of galactic governance. Who gets to make these rules? The establishment of a governing body, a United Nations for the stars, would be fraught with difficulty. Power would naturally flow to those who control the choke points, the civilizations that hold key junctions where multiple magnetic corridors intersect. Would this lead to a new form of interstellar feudalism, with corridor lords taxing all who pass through their domain? Or would humanity find a way to create a truly representative and fair system, perhaps one where votes are weighted by a system's population or economic contribution, even if the voting process itself takes centuries to complete? The political landscape would be a complex web of alliances and treaties, all negotiated across unimaginable distances and time delays. The stability of this entire grand enterprise, the dream of a connected galaxy, hinges not just on the strength of our magnetic fields, but on the wisdom, fairness, and resilience of the legal and social structures we create to manage them. The rules of trade must be as enduring and well-designed as the trade routes themselves, for they will determine whether the interstellar age is one of peaceful cooperation or perpetual conflict. This entire breathtaking vision, from mapping the galaxy's magnetic fields to constructing the first interstellar way stations, hinges on a resource far more precious than any exotic material or energy source: the human mind. The grandest technological blueprint is meaningless without the curiosity, creativity, and dedication of the people who will bring it to life. And those people are not yet in university labs or corporate research centers. They are in classrooms today, their imaginations waiting to be ignited by a future that feels as vast and full of promise as the cosmos itself. The single most important infrastructure we can build for this interstellar future is not made of metal or superconducting wire, but of inspired young minds, and that construction begins with a fundamental shift in how we approach education. The challenge is that our current educational systems are often structured around siloed disciplines. A student might excel in physics, but see it as separate from the ethical dilemmas of artificial intelligence, or master computer programming without understanding its application in astrophysics. The concept of magnetic corridors shatters these artificial boundaries. To even begin to understand this idea, a student must become a polymath. They need physics to grasp electromagnetism and plasma dynamics. They need engineering to conceive of the stabilizer stations and magsail designs. They require computer science to program the resilient AI pilots and the robotic construction swarms. And crucially, they must engage with philosophy and ethics to grapple with the profound questions of cosmic stewardship, interstellar law, and the societal impact of such a transformative technology. This isn't just about learning individual subjects. It's about learning to see the invisible threads that connect them all into a single, coherent picture of a possible future. Educational programs of tomorrow must actively foster this interdisciplinary mindset, creating project-based learning where students work in teams to solve scaled-down versions of these grand challenges, mimicking the collaborative environment they will encounter in their future careers. The power of the magnetic corridor vision is that it provides a narrative, a story far more compelling than any abstract equation or isolated scientific principle. It transforms the study of magnetism from a chapter in a textbook into the first step in building a galactic civilization. Suddenly, solving a complex physics problem isn't just about getting a good grade. It's about figuring out how to keep a starship on course 100 light years from home. Learning to code isn't just about creating a simple app. It's about writing the fail-safe algorithms that will guide humanity's first cargo to another star. This story gives students a why, a grand, meaningful goal that imbues their studies with a sense of purpose. It answers the perennial question, when will I ever use this? With the most ambitious answer possible, you might use it to connect worlds. This narrative is a powerful tool to attract a diverse range of talents to STEM fields, showing that science and engineering are not cold, impersonal pursuits, but the essential tools for writing the next great chapter in the human story. Fostering this sense of wonder, however, requires more than just updating curricula. It demands a change in the very atmosphere of learning. It means filling classrooms with posters not just of the periodic table, but of artists' conceptions of magsail ships riding luminous plasma currents. It involves using virtual reality simulations that allow students to stand on the hull of a robotic constructor as it assembles a field stabilizer in the void. It encourages science fair projects that challenge students to build miniature magnetic sails or design simple algorithms for navigating a simulated corridor. The goal is to make the future feel tangible and achievable, something they can actively play with and contribute to, even in a small way. This approach cultivates not just knowledge, but a deep-seated passion for exploration and problem-solving, the kind of intrinsic motivation that drives innovation long after formal education has ended. Ultimately, this educational imperative is about legacy. The scientists and engineers who will design the first interstellar probes are likely already born. The ethicists who will draft the first articles of the Lex Galactica might be in middle school right now, learning about justice and fairness on their own playground. Our responsibility today is to hand them the torch, to provide them with the inspiration, the tools, and the interdisciplinary foundation they need to carry the dream forward. We must encourage their wildest ideas, answer their endless questions with patience, and show them that the greatest adventures are not in the past, but waiting in the future they will build. By planting the seeds of cosmic ambition in the fertile ground of young minds, we are not just teaching children, we are nurturing the architects of an interstellar humanity, ensuring that the journey to the stars continues long after we are gone. This vision of magnetic corridors offers us more than just a new way to travel. It presents a fundamental shift in our relationship with the universe. For so long, we have seen space as a hostile emptiness to be crossed with grit and speed, a series of daring sprints into the unknown. But this concept invites us to become builders, not just explorers. It asks us to think not in terms of missions but of legacies, to construct something that will outlive us, our nations, and even our current understanding of civilization. The immense patience required to weave this network across the light years forces a kind of humility and long-term thinking that our species desperately needs to cultivate. It transforms the cosmos from a frontier to be conquered into a home to be carefully furnished, connecting our far-flung future descendants with pathways of light and force. This is the ultimate promise, not just reaching the stars, but truly making them part of our community. And while the scale of the challenge is beyond anything we have ever attempted, it is crucial to remember that every great human achievement began as an implausible idea. The cathedrals of Europe took centuries to build, with architects who knew they would never see the final, soaring spires. The first transcontinental railroad must have seemed like a madman's dream, a thin line of iron proposed across a continent of unmapped mountains and deserts. Yet, in both cases, the vision of a connected future was powerful enough to motivate generations. The magnetic corridors are our generation's cathedral, our continental railroad, but on a canvas as vast as the galaxy itself. The challenges in energy, robotics, and physics are not walls, but simply the next set of mountains we are meant to climb. Each one represents a frontier of knowledge that, when crossed, will not only enable this future, but will undoubtedly revolutionize our lives here on Earth in ways we cannot yet predict. So as we look up at the night sky, let's try to see it not as a static tapestry, but as a dynamic map yet to be filled in. The distances are vast, but they are not empty. They are threaded with invisible currents, waiting for a species clever enough to learn their patterns and brave enough to build upon them. This journey will not start with a thunderous rocket launch, but with a quiet decision in a laboratory, a breakthrough in a material science paper, or a spark of inspiration in a young student's mind. The first step is to believe that such a future is possible, to share these ideas, and to foster the curiosity that will fuel the long work ahead. The story of humanity among the stars is still being written, and it begins with the choices we make today to look beyond the horizon, not just for a year or a decade, but for 1,000 years to come.